In this example, I would like to take a look at the mean value theorem for integrals, and I would like to apply it to this function f of x equals 1 over x over this given closed interval 1 to e squared, and find this value of c that the mean value theorem guarantees exists. All right, so we have one kind of main prerequisite before we can use the mean value theorem for integrals. We need to ensure that this function is continuous over this closed interval. Well, the function 1 over x only has a single point of discontinuity, and that's x equals 0, and that's in the form of a vertical asymptote. But you'll notice x equals 0 is not in our closed interval. So in fact, this function is continuous over the entirety of the interval, which is good. So let's go ahead and kind of remind ourselves of this mean value theorem for integrals. We have a definite integral on the left side. And remember, when you evaluate a definite integral, you're actually finding the area of the region, and in this case, it's bound above by our function, 1 over x, and bound below by the x-axis. Okay, and on the right side, it looks like we have a product. We have this f of c, which is a y value, and this b minus a, which is a width, so that's kind of our x value. So really what it is we're doing, we're taking this region, which who knows what the shape of it is right now, I'll show you a graph here in a second, and we're smushing it down into a rectangle. The width of that rectangle is the width of our interval, and the height of that rectangle is actually this f of c, which comes out to be the average value of our function. But it's the c value that I'm looking for, okay? Because the mean value theorem says that there's an x value that exists, we're calling it c, and this x value, whenever you plug it in, you actually get the average value for the function. Okay, so let's go ahead and start by taking a look at the graph of this function, and I'll show you what the function looks like, and then as well the region that we're trying to evaluate the area of. And next, let's go ahead and just take a quick look at the picture of this area once we smush it down and it looks like a rectangle. Well, all right, now that you have a good visual idea of what it is we're trying to do, let's go ahead and do it algebraically. Okay, so we're going to do this definite integral, and it's going to be from 1 to e squared of our function 1 over x with respect to x. And so this is not bad at all because the integral of 1 over x is actually just the natural log of x, and we're going to evaluate that from 1 to e squared. Alrighty, so let's go ahead and plug this in. We have the natural log of e squared minus the natural log of 1. Okay, so moving up here, well, the natural log and the e cancel each other out, and so we're left with just 2, and then the natural log of 1 is 0. So we're saying that the area of this region is going to be 2. All right, so looking back up here, we just evaluated this definite integral. So we have 2 equals, and I'm going to put this down here. We have this f of c, and then multiplied by b minus a, which is e squared minus 1. So two things need to happen. The first is we need to solve for f of c and kind of get that y value, and then set it equal to our function and find the x value from which it came. Okay, so let's go ahead, we'll divide both sides of this equation by e squared minus 1, and that will give us our f of c, which is 2 over e squared minus 1. And remember, this is kind of that y value, or the height of this rectangle. And so when we take that y value, we will set our function 1 over x equal to that y value. All right, and now let's just solve for x. Well, it looks like if we reciprocate both sides, we'll end up with x equals e squared minus 1 over 2. Okay, and that actually is that C value that's guaranteed by our mean value theorem for integrals. So this is an ordered pair, and this ordered pair is the x value, so e squared minus 1 over 2. And when we plug it in, we get our y value, so 2 over e squared minus 1. And yeah, they're just reciprocals, right? Because our function is 1 over x. So let's go ahead and take a look at that ordered pair on the graph, and our horizontal dashed red line will be the average value of our function, and that's also the top part of our rectangle, that top edge. And the ordered pair will be not only the x value where that occurs, but the y value where that occurs. So all those things intersect. So here's what that graph looks like. Okay, so that example then, we use the mean value theorem for integrals. We went ahead and we evaluated our definite integral, and we knew our limits here are b minus a, and so we solved for this y value, which is the height of our rectangle, this f of c, and then we went ahead and set that equal to our function and found that c value that's guaranteed by our mean value theorem.